Hi, how's it going? I don't know, happy Valentine's Day, I guess. This is probably the last really serious ray tracing video that I'll do for a while. I will come back to it. So ray tracing is reasonably complicated, and in this video I'm going to go through a scene which has multiple models, but each model has its own model transform. Currently, this is only using one model. However, it should be pretty straightforward to apply modifications and get multiple models loaded. But the challenge is, how do we reuse the data from the one model at different transforms? So when I was debugging this is a scenario that I went through. We have our axis, we probably have our viewer, there's the camera, and we have a series of planes. Okay, so I went through this step by step, and then I realized that it just either sounded crazy or it was just spending too much time explaining a basic thing. So here's a test case. We have a camera here just behind the origin, and we have 6 planes laid out. Now each of these planes is an instance of this model, which has been loaded with 2 triangles. And when we make that model, we construct an acceleration structure. This is called a bottom level acceleration structure because it gets down to the raw triangles of the thing. So see here, we started with a node of 0 and then shifted it to 11. I'll talk about that in a second. But when we trace the ray, we do need to have a smart way to look through space. That's where the top level acceleration structure comes in. A top level acceleration structure just divides space, and the underlying primitives are not triangles, they're instances of a bottom level acceleration structure. So let's say I shoot through and I hit bottom level acceleration structure index 0. Just like with the spheres, when these acceleration structures were constructed, things were reordered and shuffled around, and so we need an indirection table, just like the sphere index buffer. So we look in there and we say, okay, thing number 0, that's actually description number 5. And then we have another buffer which describes each of the instances. We need to know the index, in this case 5. We need to know the inverse model transform, which describes how it relates to the world. That's some 4x4 matrix. And then we need the node index. So back to that 11. If I have 5 instances and I make a binary tree out of them, then the theoretical maximum number of nodes I would need would be 11. Now the reason I shift the root node of this bottom level acceleration structure to 11 is that all of these nodes are going to be stored on the same buffer. So I'm going to reserve the first 11 spots for the top level acceleration structure. And it's okay if some of them are garbage, that's fine. But then from 11 onwards, the BLAS will begin. And the reason I'm reserving all that space is if things move around, I can safely reconstruct my TLAS. But anyway, speaking of TLAS, TLDR, let's get into the code. Okay, let's get into it. Now, this is going to be quite a slog, and I'll do it over a few sessions, but if you open up the GitHub repo, head to the start folder. I've actually got this set up with some to-dos. So for instance, if we open up the shaders, I've got a bunch of to-do items. And additionally, I've got a to-dos file, which has a recommended order. So if you want, you can pause the video now, just open up the GitHub, start working through, see how I'm going as well. I think there's a lot of value to having a go at things for yourself. Also, these to-dos were written before I did the debugging, so there might be some minor variations, so do check back in. But anyway, with that out of the way, let me start. And in this session, I'm going to have a look at the ray tracing kernel. So let's just open that up. So everything here looks okay. Yep, sphere. I mean, we're done with spheres. Maybe we'll bring them back later, but for now, that's fine. Yep. Okay. Make a struct to declare the bottom level acceleration structure to describe. We'll need both an inverse model matrix and an index into the root node. All right, so let's get on this. Make a struct, and I'm going to call this a BLAS description. And we'll have the inverse model and the root node index. What I'm going to do is just make things easy for myself. Okay, this has been hard enough. So I'm just going to get around any alignment issues by copying the same data 4 times. Why not? I'm not using it for anything else. Okay, now to do, make an array of BLAS descriptions. Okay, no worries. So we'll do it the same way as we do here. Yeah, BLAS descriptions, and we'll have descriptions will be an array. Just like I was saying in the descriptive part, the BLAS description describes an instance of a model somewhere in the world. The inverse model matrix describes how it relates to the world, and the root node index is used because all of the nodes, be they top level or bottom level, will be residing in the same buffer. So we need to know where to start looking for the model. Remove the inverse model, and while we're at it, the primitive count. Yeah, because we're not using that anymore. Okay, no worries. Done. There we go. To do is to done. Okay, remove the position field. Too easy. Okay, so add a bottom level BVH and another storage buffer to track the bottom level BVH lookup. Okay, no worries. So let's go through this. We have the color buffer, and then the scene, and then the objects, that's the triangles, and then the tree, that's a set of nodes which will have all of everything, top level and bottom level. Maybe after this. So we've got the set of descriptions of the instances. Now, if it looks like I'm going slowly, it's because I don't want to, what did I say in my other video? Life's too short for debugging. It is too short for debugging. So then I'm going to add the lookup. Okay, so we can actually reuse that same object indices. Why can I not speak? Because it's an array of float 32. It's the same thing as the triangle lookup. So then I'll just straighten out these bindings. Okay, to do, remove the object array. Yes, the transform is not being applied at this point. At the top level, we just have no transform, just the identity. Call the top level trace function. So if I go down below, I've split this off. We have a trace top level acceleration structure and a trace bottom level acceleration structure. So what I want to do when I start out in the scene is at the top level, and I want to pass in the world array. Okay, the rest of this is fine. I can just get rid of this object array down here. There it is. I'm happy with that function. The top level is really not going to change too much. The goal is to trace through the boxes and get down to a box which has a bottom level structure in it. Okay, so I'm happy with all of this. I'm actually going to remove this to do. This was before I started debugging. We could store nearest hit as a field within the render state, but what's the point? Likewise, I had a separate thing like TLS nodes. No, this is fine. We'll just get rid of this. And note that I have widened this stack. It probably doesn't need to be this big, especially not for the top level. This is overkill for the top level, but this part hasn't caused a performance issue, so I'll just leave it there, give myself plenty of space. Yep, we can totally get rid of this. This is not an issue. Nah, this is fine. Because it's doing the same thing, whether it's top level or bottom level, it's just tracing a whole bunch of boxes. So now we need to not hit triangle, but trace the bottom level acceleration structure. Here's what I'll do. We'll pass in the array, and then I need those descriptions. So I'll look in there, and I'll indirect with the BLAS lookup, and that should be fine. I will get rid of the, because this, I don't need a near test. Yep, just double checking my finished notes. That is fine. So let's just completely get rid of that to do. That's not necessary. Give the function the following arguments: BLAS description and render state. So okay, so what I'll do is if we get to a bottom level acceleration structure, that's the point at which we apply the object transform matrix. So I'll just, oh no, I removed that. Okay, that's fine. I'll set this up again. Okay, cool. So the array is transformed. It's ready to go. And then make a copy of the render state argument so it can be modified by this function. Set hit to false, as this is the first ray tracing function which uses triangles. Well, actually, we set hit to false because when we come back, we only overwrite something if we hit something. So we can pretty safely set it to false. Okay, so fetch the root node according to the BLAS description. Yeah, get one component of the root node index and use that. Okay, I'm gonna resize that to 20 nodes. Why not? Okay, so we're going through here now. This is super important. See, I missed this the first time. This is probably what made so much drama, but we need to, every time we call a trace function, we need to pass in the transformed array. We don't need this. But we should be making a copy. Okay, just 1 second. Yep, cool. So we've got a copy we can modify. Okay, so again, I've gone through the acceleration structures in past videos, but this branch here is essentially just checking the internal nodes. When we get to this branch, then we're checking the external nodes. So to do return nearest hit, I don't necessarily agree with that. Let's get rid of that. Okay, so we want to hit a triangle. We're going to pass in, of course, the transformed array, and then we'll get the appropriate triangle. That's what this line is doing. That's fine. And then of course, our local copy, the BLAS nearest hit, and then the render state. And then we're going to need one more thing, and that is we are going to need to pass in the inverse model transform. And the reason for that is later on in the triangle function. But we will need to get rid of, okay. I'm derailing myself because we removed position from the render state struct. We will need to not set that. And then down here, this line now won't work, so we can just comment that out. Maybe we'll look at that later. But yeah, so we can leave that. Anyway, where was I? In the triangle, when we set the normal, we do need to invert the inverse model. And for that reason, we need to take an inverse model as an argument. Yeah, we do need the nearest hit. And then, by the way, remember, again, maybe I'm just spending too much time to explain a basic thing, but back in the top level function, the top level's nearest hit parameter will only be set if we hit something. So hopefully there's enough safeguards to stop weird things from happening. Who knows? To do, remove tmax. No, we can keep it. Oh, but I already did. But let's put it back in. Okay, so just make this a little neater. So we have the ray, the triangle, the tmin, and the tmax, the old render state, and finally the inverse model. Now what we could do at this point, I flip this around. If we had a normal that we were like looking at the back face of a triangle, what I did is just flip the normal around so the back face would become the front face. However, now we're doing models which are closed systems when we'll never be looking at the back face of a triangle, and we're not shooting our ray through the triangle. We're not doing refraction. So what we could do is return at this point, just to speed things up a little bit. This is fine, we don't need to do this line. I'm not sure if I talked about it before, but with the render state, we don't need the position variable anymore. It's all about t. That can be recovered by looking at the world ray, not the object ray. But anyway, then we get the normal, and now we can just use that inverse model argument, which was provided in the function. So yeah, I think that's fine. And likewise, this AAB function is fine as well. Okay, so I know that was a bit of a slog, but that was a little crash course in the raw data that the shader will be dealing with. You can see, again, just to really summarize things, we have two levels. We have the top level, which talks down to the models, and then we have the bottom level, which is actually the model itself. That'll be it for now. We have completed this item. We can go to our to-dos and say Raytracing kernel. That is done. All right, so I just want to make a few corrections to that code that I just wrote. As I looked back over the footage, I realized I made a few mistakes. If we go to the trace bottom level acceleration structure, see that we're taking in, the nearest hit as a float, and we're copying it over, making a copy so we can modify it. But in the meantime, we're sort of redeclaring it. So that's definitely going to mess with things. We should remove that. And then secondly, it comes down to the triangle tracing. So imagine that we shoot a ray and the ray tests against a bunch of triangles. And unfortunately, the triangles are tested in the worst order so that it sort of succeeds a number of times, but then overwrites. What we want to do is not, well, first of all, so don't transform the triangle every time we hit something. Don't transform the normal. We only need to transform the normal after we've tested the last triangle and confirmed that we've hit something. And then the other thing I was going to say is passing in a 4x4 matrix as an argument is just an extra computational overhead. It's increasing our memory bandwidth. So let's get rid of that argument. And of course, we'll get rid of it here in the hit triangle function. And look, I don't know, maybe that's fine, but you know, the things you spot when you record yourself and then watch the footage. Okay, so what we're doing is right down at the bottom, this is assuming that we've hit the triangle. Awesome. Now I'll just take this line. Oh, no, do not do that. I'll just take this line and copy it. What? All I'm doing is accidentally hitting my mouse pad. Why does hitting my mouse pad open dictionary? That makes no sense. That's just a mystery, I guess. Okay, so let's say we do all of our tracing and we have hit something. At this point, we can transform that normal from object space into world space. There's no reason to do it a bunch of times. Okay, cool. So at the end, finally, whatever we had there, we transform it. Now, in the meantime, for the hit triangle function, right down the bottom, what I want to do is take this. This is the interpolated normal in object space, and I'll just store that as the render states normal. Okay. So hopefully I haven't missed anything else, but those were the two major things I wanted to go over. Let's head back to the to-dos. Okay, so in the next part here, we're dealing with the object mesh file. I'm going to break it into two parts. First of all, well, I'll do this in reverse order, but one thing we'll do is the object mesh. We'll need to pretty much just store the model data and build its own bounding volume hierarchy. We can grab the code from the scene class to do that. And then the statue object is going to take care of basically the transform. So what we'll do is we can just pop over, make a new file. I'll call this statue.ts, not st, and I'll just grab the object mesh code, all of that, and paste it in. And triangle, we don't need that. We do need degree to radian. We don't need vec2 because we're not dealing with texture coordinates. So this class will be, I'll call it statue. We don't need any of this model data stuff. And I'm actually not going to store the inverse model either. I'm going to store the original model. Now, yeah, similarly, we don't need any of this. That's fine. That's it. We're just tracking the position and the Eulers. So these notes are really for the object mesh. Just take a big sledgehammer to all this code. When I'm refactoring code, the first thing I do is just remove, and then the second thing I do is add. That's my general philosophy if I'm doing a lot of work. It's always remove and add, because generally you won't get in trouble. Well, I mean, maybe you get in a little trouble, but generally removing things is simpler. Okay, so that is working fine. And then update is perfectly fine. Calculate transform, okay. We will not invert, we'll just store this. Now, this is one of my little pet peeves is when I was running this, I found that for some reason, the matrices don't act properly unless you translate first and then rotate. And I really hate that convention. If you know anything about matrix transforms, you know that typically if you want to spin around the axis, you would rotate first and then translate. It just sort of looks like a lack of understanding of how matrix multiplication works. But hey, tell me if that's too harsh. Anyway, so we don't need any of this stuff here. We can just completely get rid of this read file, read corner, read vertex, all of that. Excellent. So like I said, the statue is really just describing an instance of a model. It does not hold any model data, just the transform data. That is fine. We can close that down and have a look at the object mesh. So this is going to be a little bit more involved. So by the way, we can go and remove the statue because we've set that up. So now we want to read a file, make the triangles, and build the bounding volume hierarchy. So why not speed things up? I'll just go over to the scene, grab all the bounding volume hierarchy stuff. Okay. So we'll remove the degrees to radian function, import node. Then we'll just follow these steps. So remove the inverse model, triangle, that's all fine. Remove the position and Eulers. And then we're going to need to add the following. So we'll add triangle indices. I'm really just duplicating the work that I was doing before. And we'll add nodes. That's a list of nodes. Then we'll keep track of nodes used. And we'll have min and maximum corners. For the constructor, we do not need to take the position and Eulers because, like I said, we're just loading a model file. Similarly, we can remove all of this stuff. And like I said, if I'm refactoring, the first thing I'll do is remove and then add. So I will leave this bit for now. Remove the update function, yes. Remove the calculate transform, no worries. And that's probably where we're at for now. Okay, let's initialize the min corner and max corner to impossible values. So what that means, of course, is I'll set the min corner to something which will always be overridden. 1, 2, 3, 4, 5, 6. We can actually clear those arrays for V, VT, and VN because the data which was loaded there has already been used. So we can say, clear this to a blank array. Now we can build the bounding volume hierarchy. Read file, nothing needs to change there. Read vertex data. So what I want to do is as I load the file, I want to keep a track of basically how big would the bounding box around that file be. And a great way to do that is as we get vertices, as we get positions, update the corners. So what this is doing is comparing the new vertex which has just been loaded in with the current minimum coordinates and reducing those minimum coordinates if needed. And then we'll do the exact same thing with the maximum so that we will be growing the maximum coordinates if needed. Normal data, read face data, that's all fine. Now, a lot of the notes which I've got here are relating to the usage of this function in the scene. So I'll just be a little judicious here. I'll just give a default value for nodes used. Yeah, so just ignore these to-do notes. Those are for the scene. So instead of, yeah, triangles length, that's fine. I'm just allocating the triangle indices data without any reordering currently. So that's just set to nothing. I don't need to worry about this BLAS description. That will be for the scene. And similarly, I'm not going to worry about this one here. So like I've said in past videos, the theoretical maximum number of nodes required is double the array size -1. So that's why I'm setting that array there. And I could increase by 1. I'm actually just going to, it doesn't make a single bit of difference. Okay, so nothing needs to change in that function, I think. Then we look at subdivide, and I am just going to make a quick change here. So I'm going to change this condition to less than 2 because I don't want to have a bounding box with 2 triangles together. That's a little bit wasteful if we don't need it. But otherwise nothing here has to change because, yeah, as I said, we are literally just shifting this code over. So yeah, that code can come in with no real alterations. We'll head back to our to-dos, and I think that is it for the statue file. All right, so that is most definitely not it for the object mesh. I just noticed when I was recording this that I set some dodgy values in the constructor. So these should all be negative. They need to be impossibly small, of course. But now, hopefully, that is it. So the next thing we need to do is make a BLAS description file. It needs to store a min and max corner, an inverse model transform, a root node, and a center. The center will be used for the bounding volume hierarchy construction. So let's go ahead and add, oops, probably the wrong place to add it. Oh, definitely not there. Let's add this BLAS description. And I'm just going to write this from the top down. So we're going to need some classes. We're going to need a mat4 class to describe the inverse model transform, and we're going to need vec3 to describe the extent. So we'll set up this class. For the class members, we're going to have a min corner, max corner, a center, an inverse model, and we can give that a default value since we'll simply be overwriting it every frame. We're also going to give a root node index. So this is all going to be in the constructor. The constructor will take some corners and a model transform. So the first thing I'll do is just initialize the min and max to impossible values. And then I'll make a variable called corner. Okay, so the idea is that we've got this axis aligned bounding box which has been hit with some sort of model transform. And I want to understand what is the new axis aligned bounding box after applying that transform. So what I'm going to do is I'm going to apply the transform to all 8 corners of the box. And we get those corners by working with all the combinations of the min and max dimensions. So this will just take a second. I'll set this up. So that represents the 8 corners of the original bounding box. Now what I'll do is transform each corner and fetch its, compare the min and max corner to the transformed corner. So with that set up, we can then take the midpoint between the min and max corners, store that as the center of the box, and also invert the model transform which we were given in the constructor. Okay, excellent. So there we have it. That is the constructor for our bottom level acceleration structure description. We can cross that off. Actually, it wasn't too hard. But the next ones are going to be a little more involved. Okay, let's see if we can power through. We have 2 files left, so I'll just close down these other files. Let's have a look at the scene. And we have a whole bunch of things here. Okay, so let's start from the top. We'll import the statue and BLAS description classes. Yep, we can absolutely get rid of the triangle count variable. And this will give us a few errors. So then I'll just go down and everywhere I see triangle count, I'll just replace it with this triangle's length. So we can get rid of this one here. We're going to add a BLAS indices list and a BLAS descriptions list. Alrighty, so then we'll add a list of statues. Okay, so we load the model and then we upload the data from the model, but we don't want to upload the data every frame, only once is fine. So I'll just make a variable, I'll call this BLAS consumed. Now, just a side note, if you're looking through the finished code for here, I have a bunch of print statements in here as well, which are controlled by another variable. And I thought I would leave that in there just for this bit of code, because it's I think it's good to show a bit of debug code. You know, when I write one of these code things, it's an hour of presentation maybe, but then it's like a full, maybe sometimes days of preparation and debugging. So it's just important to keep that in mind. Like, this stuff doesn't just spring up from nowhere. It's a lot of suffering and debugging to get it working. All right, so I'm going to ignore triangle count, and of course the main file will now have a problem because let's completely get rid of that variable. We'll just construct the scene, no worries. And then similarly, we'll take the scene, triangles, length, something like that. Oh, here's another thing we can do. Let's multiply that by the number of statues. So this will actually be the number of triangles in the scene. Okay, yeah, that's a good idea. Okay, that's fine. I'll close that down. Where was I? Right. So for the statue mesh, we don't need to describe any parameters. We just load it. Now let's make a bunch of statues. So there we have it. We're sort of creating a uniform grid of statues, which are all standing out in front of the camera. And I'm just going to shift this camera up a little bit. Yeah, I know it's weird that negative is up. I should probably address that, but it's not a big deal for now. Okay, so then I'll go down, and of course this should be statue mesh. And then what I'll do is I'll grab all the triangles from the statue mesh and put them into our set. And we could probably then set the statue mesh's set of triangles to a blank set. I'll just leave it there for now. Okay. Right, so now we'll update all the statues in the update function. Actually, sorry, before I get to that, just in the make scene, there is a little bit more that I want to do. So I'm going to calculate, let's give myself another variable up here. We'll say TLAS nodes max will be a number. So it's important to keep track of the maximum number of nodes which must be allocated for the top level acceleration structure, because in the nodes buffer they'll be allocated first, and then we also need to know where the padding will be. So we'll just calculate this right now. So the maximum node count will be 2 times the number of statues minus 1. And then I'm also going to keep track of the number of bottom level nodes. And whereas with the top level, we keep the theoretical maximum reserved, for the bottom level, because the model is loaded and calculated and that never changes, we can just read off the actual number of nodes which we used. So we go this stat. So we'll pre-allocate the nodes. And what I'll do right now is just run through that whole list of nodes, create a blank node for each of the elements, and zero out all of the members. Okay, cool. So it's important to construct all of this and zero it all out once. Typically we do it in the BVH builder, but this BVH builder is going to be run every frame. Because I don't have a massive number of models, it is acceptable, I would say, to continually be rebuilding at the top level. And long story short, in order to do that, we need to allocate the nodes once in the constructor. So what we can do now is I don't have this right now, but I'll just declare it. So I'll build the BVH and then finalize the BVH. And then note that because the job of finalizing the BVH will be to upload all of the model data. So we can say, yep, at this point, that is all being consumed. Okay, and this will make a little more sense later on when we dive into it. I know this function is going to be a little bit weird, but we'll do what we can. Okay, so where was I? Update. So it's really not too bad. We'll just do a for each loop on our statues. And so now what we'll do is we will build the bounding volume hierarchy. So again, as a reminder, this is just building at the top level. It's not rebuilding the underlying models. It's just dealing with how objects are placed. Okay, so now let's have a look at the okay, so I'll set the nodes used to 0. Okay, and then I'm going to change these orders a little bit. It'll make sense. So what am I doing? Next thing I'll do is set up all of the BLAS descriptions and BLAS indices. Okay, so we need to pass in the min and max corners as well as the model transform. So no worries. The min and max corners are a property of the statue mesh. And the model transform is stored in each of the statue objects. Okay, so then we can set the, what is it? Oh, what? Good work, autocomplete. So I go to write description, and the first thing it can think of is describe. Anyway, so we know what the root node index is because we know how many top level nodes have been allocated. And we know that that space is always going to be reserved. So we can set that straight away. Anyway, so what we'll do is we'll record this in the list. And then because no ordering has been performed, we will just pass in that index. There we go. Okay, so that has set up all of the BLAS descriptions and indices. And then if we go back to the make scene part, up here, this is zeroing out all of the nodes. Let's run that again, but we'll just zero out the top level nodes. A lot of this is just covering my bases, making sure I'm not... It's checks and balances basically, but yeah, we'll just zero out all those nodes. Just make sure that stuff which isn't used is actually storing garbage data. We can actually take this triangle indices stuff and we can ship it up above to the constructor. So I know there's a lot of back and forth, but hey, that's just how it goes. So at this point here, we're grabbing the data. Yeah, sure. Okay. Just double checking my work. Yep, that looks good. Okay. And this is fine. I've already done that above. And yeah, because this root node needs to hold all of the BLAS descriptions, then we will set the primitive count to the BLAS descriptions length. Okay. So then similarly, we will update the bounds and subdivide. I would say this function is done. So this one's going to get a little bit simpler. As before, we set everything to impossible values. Then we go through the number of primitives. And we won't be working with triangles, we'll be working with descriptions. Now, each of these descriptions is just going to have a single min and max corner. Okay, excellent. So we can close that down. Now, likewise, I'm going to change this to a less than sign, just divide, split that acceleration structure down as finely as possible. Just checking through this. This is all fine. Okay. Use the BLAS description instead of the triangles. So, okay, no worries. So we'll say if BLAS descriptions based on BLAS indices, and instead of centroid, we'll call that center. Yeah, no worries. No worries at all. But then what we'll do is we'll just swap not the triangle indices, but the BLAS indices. I don't know, this part is going to get very repetitive. Get used to hearing me say BLAS a lot. Yeah, logic is still the same. I think the rest of this is actually fine. Yep, perfectly fine. Okay. All right. So this finalize BVH function is actually going to be surprisingly simple. All it will do is upload the nodes from the model. And then, of course, if we have an internal node, then the root node is not going to be 0. The root node is going to be whatever the first position is after all of the TLAS nodes. So we'll have to shift some of those indices around, some of those nodes. Okay, so the first thing I'm going to do is I'm going to check, is this node that I'm looking at an internal node? If it is, then we need to shift it. So we'll increase its left child by the offset, which is the number of TLS nodes which have been reserved. Otherwise, that's fine, do nothing. So what we'll do is we'll then store that in our list at position I with an offset of the reserved nodes. It might be saying, hey, wait a second. Is this going to run into trouble? Because what we're doing is we're sort of taking a reference to an object and then modifying that reference. And yeah, you're right. If we try to upload the same data more than once, we're absolutely going to run into trouble. So I guess the answer is let's not do that. I mean, we're only calling the function once. That's it's probably fine. Okay, so I think, and it's a very strong think, it's a very strong if, but I think this one might be okay. So I'll just leave that. And you know what? I'm actually going to power on through and have a look at the renderer class now. And yeah, this is sort of a big one. So we have some to-dos here. We'll have to add a BLAS description buffer. Let's go ahead and do that. And similarly, a BLAS index buffer. All right, so the constructor, that's all right. Initialize, seems okay. Setup device, yep, that's all right. Right, okay. So, to do, remember that we have got a bunch of new buffers that we're adding. So we're going to add 2 read-only storage buffers before the cube map. So if we go right down, we have our cube map here and the sampler. Let's just, okay, that should be fine. So again, I'll just straighten out these binding numbers. So we go 3, 4, and just keep counting up. Okay, right, so create assets. I'm going to have to make a few changes here. If we go down to the parameter buffer descriptor, remember that we removed the inverse model matrix, and a 4x4 matrix has 64 bytes. So we'll remove 64 bytes from the buffer size. That is, yep, that's good. Okay, now for these triangles, again, I'm going to use scene. Yeah, scene triangles length. Okay, good. Okay, now what I want to do here is update the node count. So instead of using the the nodes used, I will use the the actual number of nodes which are stored in that array. Okay, and then down below I'm going to need to make a BLAS description buffer. So what I'll do is I actually grab the code that I had above. I know this is bad naming, but that's fine. Okay, so number of bytes that we're using. Well, if you remember back to it, we're using a 4x4 matrix, and then we're using a vec4 to store the root index. So a 4x4 matrix is 64 bytes, a vec4 is 16 bytes. That'll be a total of 80 bytes per member. And this is based on the number of BLAS descriptions that we have. Okay. Then just down here, we're going to need to change this to scene triangles length. It's one of those things, just rip the band-aid off now, get it over with. And then likewise, we're going to have a BLAS index buffer. So I'll just create that. And that will be based on the number of BLAS indices. Okay. Yep, good. All right, so make bind groups. So just as a refresher, these are the bind groups that I need. So I want binding 0 to be my color buffer. Yep, I can see that there on the screen. Binding 1 to be my scene data. Yep, scene parameters, okay. Binding 2 to be the triangles. You can see what I'm doing here, so I'll just jump to the chase, cut to the chase as it were. So I want binding 4 to be my BLAS description buffer. Binding 5 to be the triangle index, and then binding 6 to be the BLAS index. Okay, well, fingers crossed, because pity me if I ever have to debug this. Spoiler alert, I'll probably have to debug it. Okay, make pipelines, that is fine. Nothing to do there. Okay, yep, let's just, I'll remove those fields. We don't need them. And what I can now do is remove this line here, writing the inverse model. That's fine. But now, because I don't have a triangle count, I'm really just going to be sending in padding. So let's just send 0. No worries. Okay. So now I'll go ahead and write the BLAS descriptions and indices. Okay, so the number of floats that we're using, we'll have 16 floats for the 4x4 matrix, 4 floats for the vec4, so we'll have 20 floats per element. All right, so for this 0 to 16 loop, I'm just writing the 16 elements of the 4x4 matrix. Good, okay, so we've written all the elements. We'll then repeatedly write the root node index. Why not? mean, we didn't have to do this. We could just write once for the first element and then write zeros, but somehow it just felt right. So with that set up, we can then write on the queue. So I'll go it's getting a little long, that line. Okay. Right. So then we just write that to the buffer. Okay. So let's go ahead and also write the BLAS indices. So we'll just write one float per entry. And yeah, the BLAS indices will have the same length as the BLAS descriptions, but let's just keep the data clean. Why not? Okay, excellent. Yeah, this is really important. I made this mistake in the past. Make sure we're writing to the right array. It's not good. It's not good if it, you know what I'm saying. Because that's an error where you get a result that almost looks right, or at least it looks wrong, but it's not throwing any errors. If I load up WebGPU and I'm getting a blank screen, then I really, really hope it's giving me errors that I can use. Otherwise, there's not much I can do. Okay. That's indices length. Okay. Fingers crossed. So then what I want to do is I want to write the nodes, but I'm going to write this in two parts. So see that I have this sort of barrier here. This is intended for only loading the actual triangle data. So what I'll do before that is I'll write the top level data. This is so important, I'll make a comment. I'll write the top level nodes. And I will use so even though, let's go with the number 11, for instance. Let's say that our system allocates 11 nodes, but our structure only uses 5 of them. No worries. We just want to write the first 5. Don't worry with the rest. So yeah, none of this really needs to change. That's fine. Yep, that's all fine. Okay. Right. So now going down, we're going to write the triangles first of all. And we'll just do the same thing as before. But yeah, that's fine. That's not an issue. That was working before. So before I wrote the top level nodes, now what I want to do is I want to write the bottom level nodes. So now I'll create this. I'll call this node data B. Why not? But this will be based on the nodes used by the statue mesh. So I'll have the scenes, statue mesh, number of nodes used. And I'll actually set that down below as well. Now what I'll do is I'll make a variable called base index, and base index will basically be I with an offset of the reserved node count. Okay. But yeah, we'll still go scene nodes, because remember, the nodes from the model data have been consumed by the scene. So they are sitting in the scenes array, just at that offset. Okay, so now when we write the buffer, if I just hover over this write function, the arguments are buffer, buffer offset. Now it says here, at param buffer offset is an offset in bytes into the buffer to begin writing at. Okay, no worries. So I'll just calculate that. I'll say buffer offset. So remember that every node takes up 32 bytes. So if we take 32 times the number of reserved nodes, that will be our buffer offset. Yeah, and then down below we'll write the triangle index data. And that was probably the most involved function. So we can close that. And I think the rest of this should be okay. Okay, so are we ready? Moment of truth. Let's see how painful this is. Let's just go ahead, start up a new terminal. We'll go npm start. Okay, but that's good because we've got a blank screen, which means there should be a legible error. So let's go and inspect. And yes, we do have an error. Alrighty. Well, this minified JS is a lot of fun to read. Okay, I hope this is it. I hope this is just it. After we create one, we need to increment I by 1. Okay. Let's see what this looks like now. Well, that was a good idea. We've still got the same problem. Okay, another issue. So in the statue file, we've got a model transform here, but this should be... Let's give that a shot. Alrighty. Something's happening. Looks like an issue on the shader side. Right, okay, line 287. Let's have a look at that. Right. Oh yeah, no worries. Alright, so we'll write to not the function parameter. I really ought to look more into pointers and references in WGSL. It is there, but yeah. Okay, no worries. I like this method. I don't like to come up with a whole bunch of things. I don't like to itemize the errors. I like to just do them one by one. Okay, so because it's satisfying seeing the number of errors go down. Right, line 303, no worries. So we'll just go down to 303. If we're using the scene, we should be using the description. Ooh. This is my favorite sort of error. We've got nothing, but we've also got nothing on the screen. Okay, another error here. I don't know if this would really make a big difference because what I'm doing is accidentally using a descriptor which has a bigger memory allocation. So that shouldn't be a big deal, but let's fix it up anyway and see if that affects the result. Okay, still not. That's fine. I've been through it head and tails, and I think, fingers crossed, I think this is it. So in the trace BLAS function, we set up a copy called BLAS render state, and that's the variable that we write to. But then right at the end, we are just returning the original render state. So that would do absolutely nothing. Again, nth times the charm. Well, that's not great. Okay, really, truly, if it's not this, I really don't know. So if we go to the renderer, so note before everything was fine, but we were just sort of seeing the shoes. So if we go to the prepare scene where we upload the data, so we've got BLAS descriptions, BLAS indices, yep. Scene nodes used, okay, so that's A, that's the top level structure. And then, yep, scene triangles, okay, no worries. Uh-oh. So we've got statue mesh nodes used, but then this loop is based on scene nodes used. Okay, let's give this a go. If it's not this, I'll eat my hat. I better not say that. Okay, there we go. So we've got, yeah, I mean, look, it looks like I'm just copying the data, but I'm actually not. I'm just very unimaginative when it comes to making scenes. So we can see that the performance isn't great, but there are a number of things we can do there. The simplest of which is simply move the camera back. So if we just, yeah, let's go to that camera and just double its distance. So we'll go -10, -2. There we go. Now the purpose of this checking it out at this distance is I just want to make sure that everything is stable, which I can see that it is. No triangles appear to be popping out of view or anything like that. Now, like I was saying, there are a number of things that we can do to improve performance. One of which is that the bottom level acceleration structure is incredibly naive. All I'm doing is just subdividing space. There is a better method called the surface area heuristic, which uses a cost function to evaluate goodness of fit. Now it is sort of taking longer to build, but the advantage is, of course, that you only need to build the bottom level acceleration structure once. And there's nothing to say that we can't simply build it offline and then write to a custom model format and then read that in and have absolutely no build time. But anyway, this is where I'm going to leave it for the time being. I'm sort of tired on this ray tracing stuff. I mean, it's really cool. It's really cool, but it is tiring. So I'll get back to the usual sort of rust and metal for a bit, and then I'll get back to the ray tracing. But yeah, no, I hope you had fun. This is sort of lots of moving parts in this session, but we got there in the end, and the result is satisfying. Anyway, I'll stop talking. Have a great time, and I'll see you in the future. Bye.